In the first section of chapter 2, recall we were determining unknown voltages and currents using Ohm's law as well as KVL and KCL. And what we're going to do in this next section, 2.1, is exploit the fact that in many cases we'll have resistances in series or parallel, especially with circuits that have many more than just two resistances, which happened in the first couple examples we did. So we'll start off by looking at this example, circuit 10, here in figure 10, and you can see that there are three resistances. Also notice that this is not a closed loop. This is actually an open circuit. And recall when we talked about the differences between short circuits and open circuits, there is no current flowing between these two nodes here, but there is voltage. And that's indicated by this V here, and it has a positive polarity at that node and a negative polarity at that node. So there is voltage across those terminals, but there is no current across them. So what we have here is we have three resistances in series. You can see they're end to end, daisy chained together. You can look at it that way. And so therefore we have one current flowing through this resistance to that resistance, indicated by I. And what we're going to do is we're going to use Ohm's law and KVL, little notation if it originally was KCL in the notes, I changed it. We're going to use Ohm's law and KVL to show that a series of combination resistances has an equivalent resistance equal to the sum of the original resistances, which means that's going to help us reduce the complexity of the circuit in terms of, for example, finding a particular current, because we could reduce all of the resistances down to a single one. Right? So we'll start off by looking at the fact that if we have three of these components, in other words, if the current is the same at all of those resistances, then we can apply Ohm's law, which we'll do right now. If we were to look at Ohm's law at each of those resistances, what we would have is, for the very first one, the voltage V1 would be, in this case, R1 times the current I. And continuing on to the second one, you would have that voltage is R2 times that same current. So what you're seeing is that the same current is showing up each time. And then finally, in the third one, the voltage would be R3 times I, right? So that's just a simple application of Ohm's law at each three of those resistances. So, and also it might be important to realize that if we look at the flow of the current into each one of those resistances, notice that the current direction is entering the positive polarity of each of the voltages. So all the resistances are in passive reference configuration, right? They're all PRC, which we know has to happen because you're absorbing energy in each one of those three resistances, okay? So let's suppose we did a KVL clockwise loop through this. So we will represent KVL through this loop, okay? Okay, now this is representative of a path because there's voltage flowing throughout this. If there was no voltage between these nodes, then we wouldn't be able to do this, but we do know that there is, so that we can do a KVL and we'll do it clockwise. So let's do a KVL clockwise application, showing the relationship between the voltages. If we're going clockwise, we're in a negative pole for the voltage between those two terminals, so that's minus V. Then we would enter V1 because they are all PRC plus V2 plus 3,3. In KVL, we know the sum of those voltages has to be 0, right? So in other words, what that says is that the voltage between those these terminals and part of the open circuit there really is just the sum of the voltages. And that's not surprising, because if the sum of those are all positive here, then this must be negative, so it's got to be balanced out, okay? All right, so what does this tell us? Well, this tells us that we could then say that the voltage, if we take this equation here and then resubstitute what each of those voltages are from Ohm's law, then that tells us that what we really have is that voltage between the open terminals there is R1 times I plus R2 times I plus R3 times I. I'm just making the substitution from Ohm's law into them. And then notice that you could factor out each of the resistances this way, summing R1 plus R2 plus R3, all times the current I. So what we've said then is that the voltage between those two nodes in this open circuit is nothing more than the sum of these resistances, noticing that they're in series. So when these resistances all in series, you can just sum them up and multiply times the same current I, right? So we can define this as what we sometimes will use an index EQ. So the equivalent resistance, REQ, is the sum. So therefore, what we've shown is that the voltage between those nodes is the R equivalent, right, times I, where that equivalent is equal to the sum. So in other words, that circuit is equivalent to this one. So we have two open nodes plus minus the voltage between them, and this equivalent resistance, which is the sum as I goes from 1 to 3 R sub I, okay? And here's the current I. So this more complicated circuit is equivalent to this circuit, exploiting the fact that the resistances were in series. So when they're in series, you simply sum them up to get the equivalent resistance, right? Okay. What about if they're in parallel? So at the bottom of the page of 27, we'll look at the next case. This one will be a little bit different because in this case, we will be looking at, we're actually going to apply KCL, with Ohm's law, but we're going to show that when you have a parallel combination of resistances, its equivalent is not the sum. It's equal to 1 divided by the sum of the reciprocal resistances, which is a mouthful of words there, but we'll see in a second what the equation looks like. And then I'll give you a trick of how to compute it in a simpler way when you take resistances 2 at a time. So if you turn over page 28, here we have that configuration, figure 11, circuit 11. Still the same setup with an open circuit here. In other words, you've got these two nodes, the voltage between them, positive polarity here, negative at the bottom. You have this one current, you have the current flowing through that voltage, flowing through from this node, and then now each of these resistances are in parallel. Notice that there are separate currents now. You won't have the same current. The current is being split across these 3 different paths, okay? All right, so Ohm's law, though, applied to this situation of each one of these, all right? Interesting, something we can note here, because each of these items are in parallel with this voltage, all right, across this open circuit here, this open segment here, these 2 nodes here. These are all in parallel, so therefore the voltage is the same across all of those. We talked about that before. When you have a series, the current is the same flowing through them. When the resistances are in parallel, they all have the same voltage. So in that case, Ohm's law applied to R1 would suggest that the I1 current is the same as the V voltage divided by R1. Okay. Again, they're in parallel, so the voltages are all shared. Okay. We're not going to make any. We talked about this. They have to be equivalent in magnitude. We're going to take the reference polarities all the same, so we won't worry about the sign differences. Okay. So that's the first one. We also know that I2 would be the voltage over R2, and then I3 would be the same voltage over R3. Again, exploiting properties of parallelism in the resistances in terms of the properties of voltage. Now, suppose we do KCL on this top node. Okay, KCL here on the top. Remember, this is to get a relationship between the currents, which is what we've done here. And if we do that, then you have, at this node, you have 1 incoming and 3 outgoing, right? So I, as the incoming current, must be equal to the sum of the outgoing currents. Right? Now, again, do what we did before, exploit another name for each one of those currents using Ohm's law that says that the current I is the voltage over R1 plus the same voltage V over R2 plus the same voltage V over R3. In other words, this time you'll factor the voltage out, which is what I'm doing. Before we factor the current out, now I'm factoring the voltage. So what this is saying is that this current flowing into the top node is, in this case, 1 over an equivalent resistance, Req, times the voltage V, where the equivalent resistance is 1 over R1 plus 1 over R2 plus 1 over R3. In other words, the reciprocal of the sum of the reciprocals, okay? Again, notice this is 1 over this. If you take 1 over this, right, it will flip this fraction. This will become the numerator, 1 becomes the denominator, which is equivalent to that. Just a little algebraic trick there. So in this case, this circuit above is equivalent, let's write it over here just so next to it, is equivalent to this circuit, right? Two open terminals. Here's the equivalent resistance, Req, and I'm just going to write it in terms of the 3 resistances we have here. It's 1 over R1 plus 1 over R2 plus 1 over R3, okay? Again, this is the voltage and this is the current I in the top. So we can take a configuration like this and render it equivalent to this. Very simple, one resistance called the equivalent resistance when these resistances are in parallel. They must be in parallel. Remember, there can be no circuit element in between these. They must be connected end to end, right? So we're just going to exploit these two properties of the equivalent resistances in the next couple of problems so that we can find unknown currents using this technique. So let's go to page 29. And on page 29, you can see we have 4 resistances with two open terminals over here, okay, that are not connected, but there is voltage, right? So the goal is to say, let's find an equivalent resistance for the following current, for the following circuit, excuse me. So let's just label these resistances. That'll be helpful in applying our formula. So let's call the 10 ohm one R1. Let's call the 5 one. I think I did this one. The 20 is R2. We'll make the 5 one R3. It really doesn't matter how we do that. Just maybe just picking some variables to represent them. Okay. And again, if we'd like to know what the equivalent resistance is for that circuit, so we have to identify properties of series and parallel. So the first thing you want to look at is, okay, what about series? Now, if you said R1, can R1 and R3 be in series? Well, not with this exit ramp here. Sometimes I'll use that terminology. You can't exit that way. You must go from one into the other, no option. So R1 and R3 cannot be in series. If you leave R3, you must go into R4, or leave R4, you must go into R3. So in that case, R3 and R4 are in series. Okay. So what that means is we have an equivalent. Maybe the first thing to do is, because you may have more than one equivalent, is maybe to index it, REQ1. So our first equivalent would be that you would sum those since they're in series, R3 plus R4. So in this case, if you sum those two, you should get what, 20 ohms, right? So what's sometimes as you get more experience with this, you'll be able to just move right on and complete the rest of the analysis simply with equations. I think getting started, it's a good idea to sort of redraw until you can see how to collapse the circuit into a single equivalent. So what I'm going to do is redraw this with what we just did. In other words, you still have the 10 ohm resistance here at the top, which we called R1. And we still have this resistance coming down here, which is 20 ohms, and we called that R2. Here's the open terminal there. But what we did is we have collapsed these two in series into a single one. So we can extend the wire out a little bit here and then drop a resistance here and call that resistance REQ1, which is 20 ohms. Okay. So these two in series have been replaced with this. Okay. And they are tied end to end to the 20 ohm resistance we called R2. So clearly, hopefully, we could see that R2 and REQ1 are in what? That's right, they're in parallel. Okay. So we would be obtaining another equivalent, we'll call it REQ2. Now, by definition, what you should do is that should be 1 over the REQ value, REQ1 value, plus 1 over R2, okay? In this case, that would be 1 over, they're both the same, right? So it's 1 over 1/20th plus 1/20th, which is what? 1 over 2/20ths, which is 1 over 1/10th, which is just 10. So it's 10 ohms, okay? That's not too bad, but I'm going to show you an alternative way. When you're taking two things in parallel at a time, there's a much faster formula that humans would probably not get more incorrectly, because it's difficult sometimes with fractions when the denominators, you know, there's common denominators. So an alternative way to do it is this way, which is actually the way I prefer to do it most of the time, is you could take the two values you're dealing with, REQ1 and REQ2. So I'll write it this way. Take REQ1, what you can do to get the same answer is multiply them for the numerator and then add them for the denominator. It doesn't take long to show that algebraically, that this fraction is equivalent to this fraction. And so that quickly says that you just multiply the two together and get 400 divided by the sum of them, which is 40, and is 10. See how fast that is? So I'll just write in words here. What's happening here is we are taking the product over the sum. When taking two parallel resistances at a time. Okay. So very important, 2. Okay. This formula does not work for any number higher than 2. Cannot do this with 3 or 4 or 5. So if you had 3, what you could do is take 2 of them at a time. Just take two pairs of the 3 elements and get it that way, right? So either way, what we've done, we've reduced this farther down to still 10 ohm resistance on the top, which is R1. But now we have rendered equivalent here, calling that REQ2, which we've said is 10 ohms. And then finally, you can see where we're going again, right? Between these two nodes, these two resistances are in series, correct? So in this case, we'll represent this as our final equivalent, but we'll say R1 and REQ2 are in series. Therefore, and we're just gonna, this is our final equivalent, so we just won't index it. So it's kind of nice to do that. So at the very end, just use REQ. So REQ is just the sum of R1 plus REQ, so 2. In this case, it's 10 ohm plus 10 ohms, it's 20 ohms. So finally, that circuit of 4 resistances on the top is equivalent to this one, 20 ohms, okay? So this is, you could say, the final reduced form. For the equivalent. So it's kind of a puzzle. It's just trying to take any arrangement that you have with series and parallels. Now we'll say down the road, you may ask the question, well, is this going to be true for all circuits? No. We'll have to go to other techniques when we can't really exploit series and parallel. But if we can, you should. It reduces the complexity tremendously, okay? So there's a nice little example of 4. Let's go on to the next example. This is just building experience of recognizing how to use this technique of series and parallel. So the goal here in example 6, page 30, same idea. See if you can find the equivalent of resistance given this circuit, and let's see what you recognize immediately here. Maybe before doing that, let's label them. The 2 ohm we'll call R1, and then in sequence we'll say the 6 ohm is R2, the 3 ohm is R3, and this final 2 ohm over here we'll call it R4. Okay. Again, I think it's best to take things 2 at a time, just so that you're less likely to get a computational error. Looking from right back to left is usually a good idea. If you're looking, because you want to look at the perspective of something that's equivalent with those 2 nodes, right? So from the right back to the left, we can immediately see that 3 and 4 in parallel. Okay. Right. So what I'm going to do is we're going to recognize equivalence and see if we can do this in sequence actually without having to redraw the circuit. Before I showed you could redraw it every time, but as you get more experience, you really don't need to do that. So we can see that Rn3 and R4 are in parallel. What is that equivalent? So let's call it REQ1. What would it be? Let's use the technique I showed you, the second technique. The values are 3 and 2, right? So 3 ohms times 2 ohms divided by 3 ohms plus 2 ohms, right? So you would get 6/5, which is 1.3 ohms, okay? Again, that's much faster than taking 1 over 3 plus 1 over 2, okay? A third and a half. So that's equivalent. So we know those 2 would be equivalent to this. And then so that equivalent then, all right, is available relative to this resistance R2. What could we say? In other words, well, we have another resistance here, cover my finger here, called 1.3 ohms. It's in parallel, isn't it? So we would have another case of parallelism. So R2 and REQ1 is in parallel. Again, if it's necessary to redraw it, then fine. But I can see quickly as I move towards the left, it's definitely going to be in parallel with that again. So we'll call that REQ2 and use the values that we would have for that, 1.3, right? Sometimes maybe it's easier to use fractions. So let's just leave it as a fraction 6/5. So we'll have 6 times 6/5 over 6 plus 6/5. And with some reduction here, so that's going to be 36/5. Getting a common denominator there. It's 36/5. Very nice. Turns out to be just 1 ohm. Okay. So what do we have? We have reduced all 3 of these parallel, taken 2 at a time, right? All of these parallel resistances to 1 ohm. And so you would have 1 resistance here. The vertical resistance would be 1 ohm. It would be in series with the 2 ohm, right? So R1 and REQ2 are in series. Therefore, the final equivalent REQ is just R1 plus REQ2, which is R1 of this case is 2 ohms, so it's 2 plus REQ 2 is 1, so you get 3 ohms. Okay, but it's a good idea that we can draw the final equivalent. So that configuration of resistances, those 4, is just equivalent to that. Okay. And again, if we knew the voltage here, we could immediately figure out the current. If we knew the current, we could figure out the voltage. That's the idea. We can reduce the complexity of finding that current or voltage by just producing the equivalent resistance. Okay. Let's move on. A couple more examples. Let's go to page 31. 7. This is an interesting topology. It's important to be able to recognize that, especially in circuit designs. You don't want, you sometimes need for spatial purposes, especially in VLSI architecture, you have to reduce the complexity of your circuit by ramming things together. So sometimes you may have resistances that may have to look like this, all right? So let's go ahead and label this situation, okay? So we have this triangular kind of structures here. So this 10 ohms, let's call it R1. Let's call the 8 ohm R2. And let's call the 6 ohm R3 and this other 3 ohm R4, okay, right? Again, find the equivalent resistance, right? The key is you can think about bending wires any way you want, even though they're triangular structure. If you can bend them out, all right, and you could produce them in a rectangular type of structure, that's fine, so that you can see what is series and what is in parallel. Keep in mind they have to be connected end to end. For example, if you took this, look at this triangular structure here. If you took this node here and just stretched it out a little bit, okay, all right, you could see that you could see a relationship between 3 and 4. In other words, it just because they look kind of funny here, if you pulled this out and maybe reduce the wires around, what you would have is this situation. Just trying to illustrate that it's possible with rewiring to look at these two things like this. Now it doesn't look like a rectangle, but you could bend that to produce that. They're in parallel, right? Even though maybe they don't look like it. Sometimes people say that you may be thinking they look like they're in series, but they can't be in series because there's a exit ramp here to go to R2. Can't have that. So R3 and R4 are in parallel. So let's get an equivalent. We'll call it REQ1. What would the value be? Both values are the same. Oh, excuse me, they're not the same. So you have 6 times 3. 6 ohms times 3 ohms over 6 plus 3 ohms. You'd have 18 on the top, 9 on the bottom. The equivalent is 2 ohms. Right? So that means this little tree structure here is replaced by a single resistance of 2 ohms. Okay, so that's what the reduction looks like right now. Now you're down to 3 resistances, and that's what it looks like. And now this equivalent is 2. Okay, so then we can say, all right, what do we know now? Well, when you leave this node and go through the 8 ohms, right, you'd be forced to come through this equivalent. So therefore, we know that R2 and our first equivalent, REQ1, are in series. Okay, so for that equivalent, REQ2 would have to be the sum, R1 plus REQ1. So in this case, it would have to be 8 plus the 2 ohms, and we would get 10, okay? So what's happened now is we've replaced this triangular with just a single one now, right? And you could say, instead of 8 there, you have 2. There's only one wire here connecting these two, this resistance and this equivalent resistance. So finally, the last resistance involved, R1 and the REQ2, would be in parallel. Again, if it helps you to redraw it, you could, just to make sure it's clear. Because again, we have taken the 3 and reduced it to 1, and there's no resistance here. So this node is connected to that node, see? So therefore they're in parallel. That's why I'm covering that up. There's just a wire, okay? So those two are in parallel. So the final equivalent has to be, let's see, it'll be 10, and the equivalent is 10. So it's 10 times 10 over 10 plus 10. It's 100 over 20, 5 ohms. So the equivalent resistance for that configuration, REQ equals 5 ohms. That's interesting. This fairly complicated looking design is nothing more than 5 ohm resistance between those two, from the perspective of those two open terminals. Okay. All right, just 2 more examples, so we can just make sure we're recognizing what we can see immediately from series and parallel. So this is a different topology. Got 4 resistances. Again, let's label them. Notice here's the 2 open terminals and interesting configurations here. The 100 ohm, we'll call this R1. This is example 8. The bottom one, 50, we'll call R2, and we'll call the 75 R3, and we'll call the 25 ohm R4. Okay. This time it's a little bit easier because you can see rectangular orientations here. And you could see that you can do things simultaneously sometimes, right? So hopefully you could see over here at the far right that R3 and R4 are in parallel. But at the same time, you notice that, well, R1 and R2 are in parallel. We don't have to do any staggered reductions there. You can see that clearly there's a current breakout here and there's a current breakout there, right? So you can go ahead and get these 2 equivalents simultaneously. So the first one we'll call REQ1, the second we'll call REQ2. Do our technique that we're using 2 at a time. So the REQ for this, the R3 and R4 will be 75 times 25 over 75 plus 25. That's going to turn out to be 75 over 4, because that's going to be 100 there. And if you want to go ahead and get a decimal, that's 18.75, right? Ohms. And the top 2, it's 150. So you're going to have 50 times 100 over 50 plus 100. And that's going to reduce to 100 over 3, which is about 33 1/3 ohms, much larger values, okay? All right, so what you would have, and maybe it's helpful to maybe redraw this one now, is these 2 are in parallel and become REQ1, correct? And then these 2 become 1, and I can draw it this way if I want. And they become REQ2, and then there's the connection back to the open terminal. And from that perspective, these are end-to-end, correct? So REQ1 and REQ2 are in series. So to get the final equivalent resistance, we simply sum. So this implies that the final equivalent resistance is just 18.75 plus 33 1/3 ohms, which turns out to be about, it's approximately 52.1 ohms. So the final equivalent looks like this: REQ equals 52.1 ohms. Okay. So this is just recognizing it. Sometimes these sub-equivalents are completely independent of each other. Not always, but sometimes, right? Almost done. And then finally, flipping over to page 33 will be our last one, okay? Just looking again, see if you can recognize series and parallel in this circuit, okay? Again, there's only 3, some larger values here. So we're gonna look at very large resistances here, okay? So we have 1K, that's again 10 to the 3rd ohms there. This will be R1. And we'll let R2 be 2K. And we'll let this one be R3. It's hard to see that, okay? 3K, right? So from the perspective of traveling, current comes in, splits out here, don't have parallelism between 1 and 3, nope. But if you leave 1, you must go into R2, right? So therefore, we know that R1 and R2 are in series. So we'll go ahead and get our equivalent, REQ1. If they're in series, you simply add them, R1 plus R2, and you would get 3K ohms, right? 1K plus 2K. So in this case, maybe we'll redraw it just so that we can see what's going on. We still have R3 here. Okay. But what we have done is we have produced another equivalent here. Okay. and we've called this REQ1, which is equal to 3K ohms. The R3 is equal to 3K ohms. And finally, you can see they're in parallel, aren't they? So R3 and the first equivalent REQ1 are in parallel. So the final equivalent, we don't need an REQ2 in this case. So the final equivalent is simply using 3K, two 3K resistances. So 3K times 3K over 3K plus 3K. Don't drop the fact that these are large values, so we're just using K. This would give you what, 9K squared over 6K. And that's the same thing as 3/2 K, or 1.5K ohms. So the equivalent in this case is just this simple circuit, with the equivalent being 1.5K ohms. So those are really good examples to sort of illustrate how to exploit series and parallel, where you find them. You just have to be very careful that, as illustrated by this example here, you have to be careful just the fact that this R1 and R3, even though they look like they might be in parallel, are they connected end to end? No, there's another resistance in between these two bottom nodes, so they're not. So we're going to take this technique and then go through a complete, what we'll call network analysis, to illustrate how to find all currents and all voltages through a resistance-based circuit in the next coming section 2.3, after a brief consideration of conductances rather than resistances in 2.2.